So, hello everybody. So, after the introductory session on the course on principles and practices of process equipment and plant design. So, there you were instructed, or rather you were told regarding uh, the different types of processes and what are the means under what conditions which processes are applicable, and then exactly what does the design comprise of, what are the basic steps of design and how you proceed about it. So, after this, today we have come to the second module where we will be discussing mass transfer processes. Specifically, we will be discussing separation processes. Now, when we say, if I will just start from the slide which Professor Ray had shown in the last in the last discussions, that what is a process, and it was said that among the different processes that he had highlighted upon, there were two specific things which were mentioned. One was separation of a multi-component material stream, and the other was that after chemical conversion of a reactor feed to products, then the products and the reactants, they had to be separated. So, we find that as chemical engineers, there are a large number of processes, both reacting as well as non-reacting, where we encounter different types of separation processes. Now, these separation processes, they are often employed for separating feed mixtures into other mixtures or relatively pure components, just like the reactor feed has to be separated from the unreacted feed has to be separated from the products. Then suppose you are recovering some particular chemicals or some particular components by using a solvent, and then you need to recover the solvent and recycle it. You need to remove water. You need to design a number of products which exploit the process of separation, or rather the principles of separation processes. A classical example of this is the coffee which is made in the espresso machine. Now, all of you would agree that this coffee is much more tasty than the filter coffee that we have. The primary reason is that at a very high temperature and pressure for a very short while, say about 20 to 30 seconds, water is made to come in contact with the coffee beans, and it leaches out specifically those particular chemicals which are responsible for the aroma and the cream and the sweetness of the coffee that is made, and it leaves behind the materials which are responsible for the acidity and the bitterness, etc. Now, a proper design of the coffee machine will contribute to a more tastier coffee. So, this is one particular everyday example where separation processes are used for preparation of products. Then definitely, see, when we have, as chemical engineers, we very frequently we deal with several sorts of reacting systems, and in all these reacting systems, as I have already mentioned a few minutes back, that we need to purify the reactor feed before the feed is fed into the reactor. We need to recover the unreacted reactants from the reactor effluents, and then they are needed to be recycled. We need to recover the byproducts, and we also need to recover and purify the products which we have obtained from any process in order to meet the specifications. Now, among the different separation processes that we use, and there are definitely some processes where we are required to separate, say, a heterogeneous mixture, say a mixture of two immiscible substances. In this case, the separation is slightly easier, I should say. We can exploit we can exploit gravity or the centrifugal force and even electrical forces, filtration, etc., and we can bring about this separation. After this separation, what we have a homogeneous substance. Now, in this homogeneous substance, it is comprised of different components. Now, if we would like to separate these particular components from a homogeneous mixture, the homogeneous mixture can be either in the liquid phase, it can be in the vapor phase, right. So, when we have to separate such a homogeneous mixture, then what are the principles that we apply? Specifically in this particular module, we will be discussing about those principles. Now, suppose we have a homogeneous system. Now, when I suppose I have say one particular mixture which comprises of say components, a binary mixture, say for example, it comprises of A and B, okay, it is homogeneous. So, now I would like to separate say B from A, either I would like to purify A or I would like to recover B from the mixture of A and B. So, what do I do in order to achieve this? First thing is, if B has to be removed from A, then I need to introduce another second phase which is preferentially going to take up B, so that B is recovered from A. Now, this second phase has to be created or it has to be added. Once the second phase it is added or it is created in any particular way, once the second phase is introduced into the mixture of A and B and I want to recover B, so therefore, definitely the second phase is expected to have a greater affinity for B as compared to A. So, therefore, the two phases they come in contact and then they are kept in for a sufficient time in contact such that mass transfer occurs between the two phases and then subsequently the two phases they are separated. So, therefore, in these processes which we will be specifically dealing with in this particular module, they are the separation processes to separate components from single homogeneous phase. So, therefore, the first challenge as we know is to create the phase. How do we go about creating the phase? Say one very conventional way which is the most commonly practiced technique in industries is by energy transfer, usually it is by heat transfer. What do we have? We have the mixture in say a particular still and we heat the mixture. We can heat it either by introducing a heating coil or by means of steam. We can heat it by any particular means. Moment we heat it, what happens? The liquid which is there, it partially vaporizes. When it partially vaporizes and the vapor is formed, quite naturally the vapor will be richer in the more volatile component. So, therefore, the vapor which is richer in the more volatile component, it rises up, leaving behind a liquid which is richer in the less volatile component. This particular vapor, it rises up, it is condensed and it collects in the accumulator where we receive a product. Quite naturally, this product is richer in the more volatile components and it leaves behind another product in the still which is richer in the less volatile component. So, this is one particular way by which a second phase has been, or rather a vapor phase has been created from a liquid phase by application of heat, and the vapor phase which has been obtained by partially vaporizing the liquid feed, it separates the liquid into more volatile components which have been obtained as a product, leaving behind the less volatile components. So, among A and B, the example which I was citing. So, suppose the mixture comprises of A and B is the more volatile component. So, definitely in the vapor we will have both A and B, but we will have a greater proportion of B here and a lesser proportion of A, and the liquid which will be lying here, naturally it will be richer in A, having a lesser proportion of B, right. Same thing we can also do by partially condensing a vapor feed. If we condense a vapor feed partially, then naturally what we get? We get the liquid which is richer in the less volatile component, and the more volatile components remain in the vapor phase. So, therefore, the creation of two phases, it can be achieved, and it is achieved most conventionally in industrial systems by majorly heat transfer. It may or may not be accompanied by shaft work, and this process it is known as distillation. There are different types of distillation which we will be discussing after we complete the introduction and certain other discussions regarding separation processes. Now, apart from energy transfer, suppose we have a liquid feed. This liquid feed, we suddenly reduce the pressure of the liquid feed is sent through, say, a throttling valve where the pressure is suddenly reduced. Moment the pressure is reduced, what happens? The liquid, it partially vaporizes, and the vapor which vaporizes and the liquid which remains, these two are under equilibrium conditions, and the vapor it is naturally it will be richer in the more volatile component, and the liquid will be richer in the less volatile component. So, therefore, the vapor composition, if generally in the vapor, the composition of the more volatile component is denoted by Y, and the composition of the more volatile component in the liquid is denoted by X. So, and by this particular process, we always obtain Y to be greater than X. So, this is one particular way of attaining separation of components from a single homogeneous phase. Definitely in this particular process, what do we get? We find that the vapor it is created from the liquid itself, and since it is created from the liquid itself, we find that the components which are available in the liquid phase, the same components are available in the vapor phase as well. So, therefore, there are no chances of the product being contaminated, but there are also certain situations where distillation is not very feasible. It is quite evident that distillation exploits the difference in boiling point of the two components. So, therefore, if the boiling points are quite far off, then definitely the vapor that we will get, it will definitely have a much greater proportion of the more volatile component. If the boiling points are very close, then definitely the separation that we will be getting, it will be much less, and under that condition we have to repeatedly perform this process. Now, suppose for getting a feasible amount of separation, if we have to use a very large number of stages, then under that condition definitely distillation is not economically feasible. When we were discussing the introduction, it has been told to you and you have realized that economics governs the choice of optimum process parameters. So, therefore, if distillation will not be economically viable, definitely we have to look for some other processes. There are also certain situations where distillation will not be feasible. For example, if the components which make up the homogeneous phase, they form an azeotrope under the conditions of temperature and pressure where distillation is being performed. If that happens, then definitely, as you know, that during an azeotropy, the vapor boils with the same composition as the liquid. So, therefore, no separation between the liquid and vapor is possible beyond the azeotropic composition. So, under those conditions, what do we do? When we cannot separate the two components of a homogeneous mixture by creating a phase, either by application of heat or by pressure reduction, then in that case we have no option, we have to add a second phase. Now, when we add the second phase, Say suppose we have got a feed, right. We add a second phase, an auxiliary phase, or the second phase we add here. It can also be said as a mass separating agent. We add it, and then what happens? This particular mass separating agent, it will definitely have more affinity towards some components of the feed as compared to the other components. So, naturally the two, the feed and the mass separating agent, both of them are introduced here, and they are allowed to be in intimate contact such that mass transfer occurs between them, and then finally the two phases, they are separated out. This is also one other way of performing the separation. Now, this feed, as I have said, the feed, it can be solid, it can be liquid, it can also be vapor or a gas. For a liquid feed, when we have a liquid feed, what is the MSA that we can add? We can add either a solid. When we add a solid MSA, then this solid, what it does? It adsorbs certain components from the liquid feed. The process is known as adsorption. Generally, during adsorption, what we have is, we introduce the feed through a solid bed. We do not introduce the solid as well as the feed together inside the bed, except under certain conditions which is known as a fluidized bed. Normally, the solid is here, the liquid flows through it, and then certain components of the liquid, they get adsorbed here, and then the liquid which depleted of those components, it comes out. We can also introduce, for a liquid feed, we can also introduce an MSA which is also a liquid, immiscible in the first liquid. So, under this condition, what happens? The liquid which has been introduced along with the feed, it again extracts some portion of the components from the liquid, and then, so naturally we get two products. One product will be richer in some components, the other product will be richer in some other components. Generally, the liquid MSA, it is termed as the solvent. This solvent, it extracts some amount, or rather some particular components more than the other components, and the product which we get, that is normally known as the extract. The extract contains greater portion of the solvent and maybe some portion of the main liquid in the feed, and a greater portion of the component which it is supposed to extract, and the remaining liquid which remains of the feed after the component has been extracted, that is known as the raffinate, which primarily comprises of the feed, maybe small amount of solvent may be there here, if because we hardly get liquids which are completely immiscible with one another. So, small amount of solvent, and this feed, it is depleted from the solute, because good amount of solute has gone into the solvent and it forms the extract. So, therefore, if we have a liquid feed, we can perform different operations. One, we can perform adsorption when the MSA is solid, extraction when the MSA is liquid, and we can also introduce a gas phase here a gaseous MSA under this condition, this is a liquid feed, under this condition again the gas, it preferentially strips out certain components from the liquid, and then we get two products, product 1 and product 2. Definitely the gaseous product will be richer in the components that it has stripped off from the liquid. So, this process is known as stripping. So, therefore, in the same way, suppose we have a gaseous feed, say the feed we have a gaseous feed. In that gaseous feed, what can we add? We can add a liquid MSA. This liquid, what it does, it preferentially dissolves some particular components of the gaseous feed are more soluble in the liquid MSA as compared to the others. So, therefore, from here we get two products, a gaseous product which is depleted from the more soluble components, and a liquid product which is richer in the more soluble components. Generally, when we add a liquid MSA, it is known as a solvent. As I have told you, this is generally known as a solvent. We can also have a solid feed. And we can introduce a liquid MSA. So, therefore, this is just the reverse of the adsorption process, and in this particular case what happens, the liquid can leach out some particular components from the solid feed, just the way water had leached out the favorable components from the coffee beans to give you the cup of coffee. So, therefore, in this particular case the process is known as leaching. Right. Here also we get two products, product 1, product 2. So, therefore, when it is not possible to create a product by addition of energy or reduction of pressure, then in that case we create the second phase by adding a second phase to the feed. So, therefore, when the feed is a solid, we can add a liquid to it and we can perform the process of leaching. When the feed is a liquid, we can add a liquid which is immiscible with the feed liquid and perform the process of extraction. We can add solid which preferentially adsorbs some particular components, and we can perform the process of adsorption. We can add a gas which preferentially strips off some particular component from the liquid feed, and this process is known as stripping. So, adsorption of water vapor from air by drying of air rather, that is a very well known adsorption process. Then dissolution of carbon dioxide from a carbon dioxide air mixture by the addition of amines or water, that is a very standard or well known absorption process. So, in this particular way, in fact, if you have a toluene acetic acid mixture and to add water to preferentially dissolve or to preferentially remove acetic acid from toluene. So, this is an extraction process. So, therefore, these are different ways by which we can add a second phase and create the or rather and we can effect mass transfer between the two phases and the separation can be achieved. There are certain things which you need to remember when you are adding the second phase. The thing is that when you are adding the second phase, then in that case you find that the products that you get, the component that you have removed from the feed, that component is dissolved or that component is in association with the MSA. So, the product that we get, that is definitely in a much more dilute form in the MSA or in the auxiliary phase. So, therefore, if we need to remove the product from here, we may encounter a costly recovery step, which definitely we have to keep into mind when we design the process by addition of a second auxiliary phase. Then quite naturally, since the product is rather the desired component is in association with the auxiliary phase, so there is chances of possible contamination of the product by the auxiliary phase. And you must remember that we need to recover the MSA and recycle it for an economic operation of the process. So, therefore, additional recovery and regeneration of the auxiliary phase has to be considered when we design such a process. And definitely in the whole process there will be some amount of auxiliary phase which will be lost, right. Suppose it is a liquid, then some amount of liquid will be volatilizing with the vapor phase. If there is some amount of vapor, then that may be carried with the liquid. So, therefore, we need to keep on having some particular makeup facility to make up the auxiliary phase which is lost by this process. And so, naturally it is quite evident that the design procedure will be more difficult and the operation will also be more expensive under this condition. So, just as distillation is complete in itself, it does not require a recovery or a regeneration system, but when we add an MSA, we need to keep this in mind. Now, here I would also like to mention that there are some other processes also which are multi-phase separation processes, but we are not considering those processes in this case. For example, suppose evaporation. What happens? There is some amount of liquid which volatilizes into the air on the vapor phase. But in this case, it is important to remember that the rate of mass transfer which occurs in this particular case, that is not governed by the equilibrium considerations. What are the equilibrium considerations? For all the processes that we have discussed, in these processes, how much amount of the component will be transferring from one phase to the other, that depends not on the concentration difference of the component in the two phases, but the difference of chemical potential of the component in the two phases. This is something which we need to remember, that for all these processes we find that the mass transfer between the two phases will occur as long as the chemical potential of the component I, say in phase alpha, suppose alpha and beta are the two phases, mass transfer will occur as long as mu I alpha is equal to mu I beta, and the mass transfer is going to stop when mu I alpha becomes equal to mu I beta. If the chemical potential of component I, it is greater in the alpha phase as compared to the beta phase, mass transfer occurs in this particular direction. If the chemical potential of component I is greater in the beta phase as compared to the alpha phase, then mass transfer occurs in this particular direction. So, therefore, in all the processes that I have discussed, we find that they are governed by interphase mass transfer, and this particular interphase mass transfer, it is governed by equilibrium considerations. There are other multi-phase mass transfer processes which are not, just like evaporation I was mentioning, these are not governed by equilibrium considerations. Say for example, drying. Definitely in drying, what happens? We have a flowing warm air and some liquid, it vaporizes here. But while we design a dryer, we do not take into consideration the equilibrium between the liquid which is evaporating and the liquid which is contained in the flowing air, because there are a lot of other things which become much more important here. For example, the temperature of the air, the velocity of the air, the rate of diffusion of the liquid from the inside of the solid to the surface. So, there are a large number of things. Definitely the liquid will continue to vaporize into the air or into the flowing gas stream as long as the vapor pressure in the flow of the liquid is greater compared to the partial pressure of the liquid in the gas stream, but this does not govern the design of dryers, and it is too difficult to get this equilibrium data. So, therefore, dryers are not designed based on equilibrium consideration. Same thing is true for heterogeneous reacting systems as well. We may have, say, suppose two particular phases where the reactants are in two phases. One reactant has to diffuse in the other phase for the reaction to take place. And in that case, we assume that the reaction is very fast, so that this interphase mass transfer governs the rate. But in this case also, the equilibrium considerations do not come during the design of the reactor. In this case, we define an apparent rate of reaction which takes into account mass transfer, but that is a completely different procedure. Same thing happens for membrane separation as well. During membrane separation, what do we have? We have got a feed. The feed is made to move through some particular barrier, maybe a porous barrier or a non-porous barrier. And what does this barrier do? This particular barrier, it either restricts or it enhances the movement of certain species with respect to the other species, and accordingly we get a phase 1 and phase 2. But again in this case, among this membrane separation process, we can have reverse osmosis, we can have microfiltration, ultrafiltration, all sorts of membrane separation processes, but they are also not governed by any equilibrium considerations. So, therefore, I repeat, in this particular module, we will be discussing those separation processes for which the interphase mass transfer occurs, and this interphase mass transfer is governed by equilibrium considerations, and therefore, for such designing of such mass transfer processes, it is important to remember that the extent of separation that we would obtain, that is limited by thermodynamic considerations, or that is limited by the departure from the or rather that is determined by the chemical potential of the component in the two phases between which the mass transfer is supposed to take place. While on the other hand, the rate of separation is governed by mass transfer. So, for the design of these particular separation processes which I have listed up here, for design of these we need to consider both transport as well as thermodynamic considerations for designing this separation operations. Now, and all these separations they are achieved because certain components they undergo interphase mass transfer by, and this particular rate of mass transfer is faster compared to the mass transfer which occurs due to bulk movement within a particular phase. So, therefore, it is important that interphase mass transfer rate is much faster as compared to the mass transfer occurring by bulk motion. And therefore, as I have told you that in all these processes what we need, we either create or add the two phases, and then mass transfer occurs in some particular equipment or a combination of equipments, and then we achieve separation. This entire process, this comprises of one stage of the separation process. What is the maximum separation that we can achieve in one stage? Maximum separation is that the two products which are two effluent products, in between these two products, the component which has to be separated, that is in equilibrium between the two phases. we cannot attain any particular separation better than this. And it is important to remember that in practice we cannot attain the equilibrium compositions. It will not be economically feasible definitely, either we need a very big equipment or we need a very long time of operation in order to achieve equilibrium. So, mostly what do we get? We can approach equilibrium, we cannot attain it. And the fractional approach to equilibrium that we can achieve in an actual stage, that is known as the stage efficiency. We will be discussing more of stage efficiency when we discuss the individual processes. So, therefore, suppose by equilibrium considerations we know that for a feed of say benzene toluene comprising of say 50% benzene or maybe 40% benzene, 60% toluene, the maximum separation that we can get by the process of distillation is say 80% benzene, but we need say 99% benzene. So, how do we do it? Definitely we need to increase the number of stages or the number of contacts between the two phases and the group, and therefore, as we increase the number of stages and we need to have some way by which the streams they are flowing from one stage to other, and the entire thing is usually housed in a tower or a column. So, therefore, the group of stages which are interconnected for flow of streams from stage to stage, this is known as a cascade. So, for any particular separation that we need to find out the number of stages that are required in the cascade. How do we go about it? We assume that all the stages in the cascade are ideal stages or equilibrium stages. That is, in each particular stage when the two phases are contacted and then when they are separated, the two phases that are separated, they have they are at equilibrium with each other. Again, you have to remember this never happens. So, what do? We find out the number of theoretical stages that are required to bring about some particular separation. Say that is denoted by n theoretical or n number of ideal stages. We know that definitely we will be requiring more number of stages as compared to the ideal stages. So, therefore, the ratio of n ideal by n actual, that gives us the overall efficiency, stage efficiency of the process. So, therefore, whenever we design processes, you will see first thing that we do is that we are given some particular specifications. This is the separation that you require. Okay. It can be in terms of recovery and can be in terms of purity. So, for that we have to find out the number of stages that we require. For finding the number of stages, we assume that for each stage the effluents are under equilibrium conditions. Accordingly, we find out the number of ideal stages, where in each stage the effluents are in equilibrium. Then we assume some particular efficiency of each particular stage. We use the data on efficiency, which are usually obtained from heuristics or they are available based on experience, and using that we find out what will be the number of actual stages. And as I have already mentioned that all these stages, they are housed in a tower, and in that tower, in order to increase the mass transfer between the phases, these towers, they are fitted with different sort of accessories. For example, we can have tray towers where within the tower there are a large number of trays which are fitted, and in these particular trays either we can have some particular perforations through which the vapor can rise and flow through the liquid, bubble through the liquid. It can also happen that these perforations, they are fitted with some attachments, etc., namely bubble caps and the valve trays are the common sort of attachments. We will be discussing these. They are just to reduce the size of the bubbles and to enhance the mass transfer. Now, in this case I would like to mention one particular thing. See, which phase should we disperse? We disperse the phases to increase the mass transfer. Why does this happen? This happens because the diffusion path decreases and the interfacial area increases. So, quite naturally we would like to disperse that particular phase which is mass transfer controlling in any particular operation. So, therefore, when the gas phase is mass transfer controlling, we disperse the gas phase. When the liquid phase is mass transfer controlling, we disperse the liquid phase. The liquid phase can be dispersed either as droplets or maybe they are broken down as thin films. And between the different cascades, the flow can be, it's mostly counter current, it can also be cross flow. When we are having one phase as the solid phase, often it happens that the solid is kept as a bed within the tower and either the gas phase or the liquid phase is made to flow through this, under which condition we say that the process is semi-continuous. So, when we opt for which process, they have already been discussed in the introductory lecture. So, I will not be going through this. So, depending upon which phase should be dispersed and how much contact we require. So, therefore, different processes most are performed in different, typically different type of equipments. So, while we discuss the processes, we will be primarily discussing about tray columns, packed beds, and while we discuss liquid extraction, we will be discussing about mixer settlers and maybe we will be mentioning something about the rotating disc contactors. So, therefore, we find that these common equipment which are used, they try to enhance the mass transfer between the phases, so that the operation can be achieved with a minimum number of stages. And you should also remember that after the two phases are brought in contact and mass transfer occurs, the two phases also have to be separated out. So, therefore, all those towers are also fitted with certain attachments which would separate liquid droplets from the ensuing vapor or the gas stream. We have some demister arrangement. There will be some arrangement where the gas has to be separated from the liquid stream. We have vortex breakers and things like that. So, when we design a column, we have to keep this thing in mind as well. For designing a column, we need to find out what should be the accessories which are required for mixing or rather for intimate contact between the two phases and maximizing the mass transfer, and also certain additional arrangements for separating the phases as completely as possible after the operation has happened. But the first thing that we require for any separation processes, for any interface mass transfer process, is data on equilibrium. So, therefore, in the next class we are going to discuss equilibrium or rather phase equilibrium for all the processes that we have discussed in this class, and after that we will be taking up each process individually and going into the details of those. So, for today this much. Thank you very much.